Hi everyone, I hope this video finds you well. I just wanted to talk you through kind of a summary of the quadratic parameters A, B, and C and talk about their implications. Of course, contextually, we had the per capita spending in our notes document, so I'm going to talk through that one briefly, but then also just to kind of summarize the overall takeaway message with regards to the story that those parameters tell. Because that's what's really cool about quadratic functions is they really do tell a story, and it's unique compared to any of the other functions, quite frankly, that we learn in this class at all. So I think it's pretty cool, and I hope that you do as well. So I'm going to go to my Desmos and hopefully, yes, there we go. So this is just the per capita spending context. I switched the variables to f of x for the sake of Desmos. Every now and again, Desmos is quirky with variables like p or t. And so just use f of x or y equals to keep it simple. That way you don't run into any issues. So, okay, so this is just, again, wrapping up what you already saw. Hopefully, my hope here is that you've already gone through the document and have already gone through the PowerPoint, and now you're just here to get the summary and the Cliffs Notes version. So, all right, here's our quadratic function, per capita spending on prescription drugs, and what do these values tell us? So your C value is the vertical intercept of the function. So in this particular context, what does that mean? It means that in 1990, people were spending $158.70 per person on prescription drugs in 1990. Okay, cool. There's your fun fact of the day. But what else was happening in 1990? So sure, we were spending $158 each on prescription drugs, but what trend was occurring in 1990? Well, that's where your B value comes in. So your B value is what we call the initial rate of change, which essentially tells you what is the parabola doing directionally, slope-wise, in the beginning, which in this case is 1990. So the fact that this particular initial rate of change is negative, you can see very clearly on the parabola in hindsight that, yeah, the slope right there at that dot is definitely negative. Initially in 1990, we were seeing a drop in per capita spending. How much of a drop? Well, $5.61. That B value is the initial rate of change, the initial slope, the initial drop in this case of per capita spending. Okay, so now we know what it was to begin with, and we know that it was dropping. Cool. But then what? Did it keep dropping? Did it not drop anymore and eventually increase? Well, that's where your A value kicks in. So your A value tells you that, since this particular one is positive anyways, it tells you that your changes in those rates are going to be positive. Since the A value is positive, that tells us that the changes in our rates will be positive or increasing. So what the tricky part here though is, remember, if it's 1.89, the actual second difference is actually twice that. Remember, it was 378 in your notes. So that tells us that 378 is going to be the increase that we see in that original rate of change. So check it out. If this first drop really is negative 5.61, well, then the next subsequent drop, notice how that second little pink dash that I made is not quite as steep as this first one. It's still negative, don't get me wrong, but it's not quite as steep. And that's because this subsequent drop is not as much of a drop as it was before. It would be 378 higher or more positive than the 561. Now notice the 378 is not a strong enough positive to overpower or overcome the negative 561. And that's why, yes, this parabola is still decreasing, but eventually, if you keep changing by an additional 378, positive 378, positive 378 against those rates, it will eventually overtake the 561. And that's why the parabola eventually does come up. this is most definitely a concave up parabola because the changes in our rates are increasing by 378. So when you take a step back and look at this parabola, you're like, okay, it's definitely a concave up parabola, definitely. But remember that concave up has two sides to that coin. So if you split this parabola right down the middle, you have the concave up portion that was decreasing because yes, the initial rate of change was negative 561. But then you also have the concave up portion that was increasing. And that's because the A value is positive, which will eventually overpower the initial negative and force the parabola to come up in its direction. So concave up overall, yes, part of which though is decreasing because of the negative initial rate of change. Eventually, of course, it becomes increasing because the positive A value eventually takes over. A calculus class gets really into this, which I think is super cool if anybody out there has to take calculus. But what I also just love about the algebra here is that we can make sense of it as algebra students. Like you don't have to have calculus to understand this. And that's hopefully what that notes document was helping you see. The A value, for instance, you saw for yourself, the second difference was 378. That didn't take calculus, that was just finding the slope. 2 times in a row, of course. It's not constant right away. That'd be linear. It's constant on what we call the second round of differences. And every single quadratic has a constant second difference. I dare you, go get any quadratic function in the whole wide world, go through the first differences and then subtract those to get the second difference. Every single time it comes out constant, and every single time it's exactly 2 times the A value. So super cool. And then same thing with the B value. Yes, that's the initial rate of change, but you saw in your notes, is it the rate of change for the entire first year? No. Even half of the first year? No. Even a tenth of the first year? Not really. It really is that we call it instantaneous moment. Like when the clock strikes midnight and it's 1990, what was the trend that we observed? Decreasing 561. So again, it's called an instantaneous rate of change. Once again, calculus phrase, but we saw it for ourselves in the algebra, which I just think is super cool. So the full story of this parabola is that yes, in 1990, people were spending $158.70 per person on their prescription drugs. Those spendings were initially dropping in 1990 by $5.61 per person that year. However, those changes, those decreasing amounts were not decreasing forever, they were increasing. Those changes, that initial change is now changing. And in this case, it's increasing by exactly $3.78 per person per year for every subsequent year. And certainly, once again, since the changes are changing by a positive amount, it eventually takes over the negative and forces your parabola to change directions. So that's the per capita spending one. I also want to, just for the sake of kind of just tying it all together, I want to also just talk through a couple, not a ton, but a couple, just generic parabolas, just so that you can really see kind of the point that I'm trying to make and how they all kind of get tied together in a similar way. So for instance, I'm just going to make up this parabola right now. So if I had a quadratic function, f of x equals, I don't know, negative 2x squared plus 7x minus 9. Totally made that up. Okay, without even going to Desmos, once again, here's what I think is so cool about quadratics. Without going to Desmos, I already have a full mental image, a story to tell about this parabola. If it were a contextual problem, I would incorporate the context. Of course I would. But this one's not a story. It's not a context. So I'm just going to do it generically. But here is what this parabola is trying to tell me. The vertical intercept is -9. So the parabola starts down here at -9. Okay, cool. Well, what's happening at that moment though? So when I'm sitting at -9, what trend am I observing? Well, the initial rate of change in this case is +7. So that tells me that this parabola is initially increasing. Now don't actually draw a line. Nope, it's not a line, it's a parabola, but hang on, stay tuned. Initially it's increasing, yes. However, what then happens to that increase? So in this particular case, notice my A value is -2. So that tells me that my rate of change is then changing. In this particular case, it's decreasing, exactly 4 units per unit. Again, if this were a story problem, we would put stories about in there, but it's not. So double your A value, you get -4. So if this initial increase is +7, okay, cool. The next increase is not going to be +7 anymore. It's only going to be +3, because +7, take away 4, +3. So it's still going up, don't get me wrong, but it's not going up as much. And then the next increment after that, this positive amount is going to drop by 4 again. And you can tell that eventually that -4 will absolutely overpower the initial +7. And so I know that this parabola will eventually be forced to come concave down. Now, what I don't know, admittedly, and this is where Desmos or of course calculus would help, but what I don't know is, just exactly how long did that take? Like, was the initial rate of change for +7, was it enough of a quote blast off to bring the parabola way up there before it came down? So like, did it actually have a chance to cross through the x-axis? Maybe. I'd have to, think about that some more, or go to Desmos, of course, for help. Or was the initial rate of change, +7, not quite strong enough to hang on, so to speak, against that -4? And did the parabola come down actually pretty quick, in which case it wouldn't have any x-intercepts at all? So that's the part where I guess admittedly the algebra falls short like just a smidge in terms of the A's and the B's and the C's. But either way, the initial value, the initial behavior of the graph, and what that graph is eventually going to do. Is it going to continue to increase and just stay on an increasing trend? Okay, perhaps. Is it going to switch into a decrease and force a concave down behavior? Perhaps. And so that's what the A's, B's, and C's tell you about any parabola in the whole wide world. And so one more just to kind of demonstrate that they don't all show their, they don't all show their vertex right away. Sometimes it's in the negatives and you wouldn't even see it, especially if it's a word problem. So here's what I mean. Let me just draw another one. I'm going to totally make this up once again. So how about f of x equals, how about -x squared, of course, minus 3x plus 7. Sure. Okay, so what do we know? Without even going to Desmos, what do we know? Well, I know that this parabola has a vertical intercept at +7. So it starts up there on the y-axis. What else do I know? I know that initially the parabola is decreasing. It's dropping. The initial rate of change is -3. So from that point, it's dropping. Okay, I'm starting to build a mental image. But now what's going to happen to that drop? Is it going to start to turn and curve up? Or is it just going to keep dropping? And in this particular one, your A value is -1, which means the changes in the rates will be -2. So whatever this drop is, the next drop is going to be even more than that. And the next drop is going to be even more than that, and then more than that. And oh my gosh, this is 100% not only decreasing, but also decreasing concave down. Most definitely decreasing concave down. And so I can't even look at that parabola right now and tell you where his vertex is, because that means it must have been back here somewhere. And so, of course, there is still a turning point, because since the rate of change is -2, that tells me that I have a concave down parabola. So I know that there's got to be a curve in there somewhere. It's just that these particular values tell me that the curve does not take place after the y-axis. Nope, because the initial drop is negative and every drop after that is still negative. So wherever the curvature was, it must have been before the vertical intercept. And so you can see, now that we've painted the whole picture, it still makes sense. Check it out way back here. Let me switch colors so that you can see the point I'm trying to make. So somewhere on the back end of this parabola, it was obviously positive. Somewhere it was positive. But since the a value is negative, the changes in my rates are decreasing. So however positive this slope is, the slope after that is not quite as positive as indicated by my a value. And then the slope after that is definitely not as positive anymore either, because it keeps dropping by -2 until eventually, whatever this slope was way back here, it keeps getting pushed and pushed and decreased until eventually, you better believe, it comes concave. I'm sorry, it turns into decreasing. It's always been concave down, but it turns into decreasing. And for this particular parabola, it's already been turned by the time you hit the vertical intercept. So that can happen too. But nonetheless, your C value, vertical intercept, B value, initial rate of change, A value, how are those changes changing, and therefore the concavity behavior of that graph. Notice every time I've done this, I've done it in reverse order. Talk about C, then B, then A. I'm telling you, if you try to tell this story in the other order, ABC, it's not going to flow well. It's not going to sound good in terms of just conversational, the storytelling component of this. And quite frankly, you might make just more mistakes. You know, I've been grading these things for 15 years, y'all. And I'm telling you, start with the C value. That's your initial value. Everything grows from there in reverse order: C, then B, then A. All right. So my hope is that we have made sense of the quadratic parameters, ABC, and you can just progress through your module, and hopefully everything is making sense. If not, you of course know where to find me, and I hope that everyone is well, and I will talk to you soon. Thank you for your time.